Okay, so we had a little halftime there, and what we took a look at is Magnum PI gave me a little bit of respite and a rest, and we've been talking about time series methods here in forecasting, and we're looking specifically at seasonal adjustments. And we said these seasonal patterns are repetitive up and down movements in demand for business. Maybe the demand for snowblowers, the demand for lawnmowers, the demand for turkeys. And these can occur quarterly. They can be monthly, weekly, daily. And we can make adjustments here depending on these past changes in the season and adjust them accordingly. And, we had said that there was a formula for this and that the seasonal factor can be divided by taking this actual demand for each season by the total and dividing it by the total annual demand as shown here in this particular formula. So let's take a look there next. And seasonal factors, again, 0 to 1, just like we talked about with probabilities before. What portion of the total annual demand is assigned to any particular season. If it would be equal, it would be 1/4, 1/4, 1/4, and 1/4 if there were 4 seasons in a year. Seasonal factors multiplied by the annual demand to provide the adjusted forecast for the period. We'll show you an example of this. So here we have different quarters, 1, 2, 3, 4 totals. So if you add all these up, it comes to 45. Add these up, comes to 50.1. Add these all up, 148.7. All the quarters, 55.3 here for quarter 4. For 98, 99, 2000, this gives us our total. And then we take a look here. Here's our demand for turkeys at this farm. For season 1, this one right here, we would take 42 divided by the total, 148.7, and it gives us a factor of 0.28, 0.20 for season 2. Notice that season 4 is the highest at 0.37. So, what does this tell us here is that we can multiply this forecast for the year by the seasonal factors. And again, so y is equal to 40.97 plus 4.30x is equal to 40.97 plus 4.30 times 4, which there are 4 of these altogether here, gives us 58.17, which we can see here in table 15.7. So here's our table 15.7, and gives us the data for which we have made our decision here, and gives us our 58.17. Again, this is bringing together here the forecast using a trend line. So we've taken our time series and we've taken the seasonality. We've come up with a trend line, and that trend line gives us a forecast for the next period, and that is 58.17. So, forecasts are not going to be, always equal to the actual values. They're going to deviate. The difference between the forecast and the actual values is a forecasting error. There's always going to be some error. We want that error to be as small as possible. And what we need to do is measure these errors. There's different methods. We're going to go over those methods to measure these errors. If it's large, the technique is not the right one. We want a small error, and we have to adjust the parameters. So, to measure these forecast errors, we have a mean absolute deviation, MAD, like Mad Magazine, mean absolute deviation. We have a mean absolute percentage deviation, MAPD. We have a cumulative error, an E bar. We have an average error, or a bias, big E. So here, let's take a look at MAD. It's the average absolute difference between the forecast and the actual demand. What's the difference? We forecasted, we got an actual. What's the difference? We want that to be small. This is very popular. It's very easy to use. The mean, the average absolute difference here is the summation of dt, the period in time t, the demand for it, minus the forecasted for the future period t, and n is the number of periods, t is the time period. So let's take a look here at the example we have for these in 15.8. Right there is 15.8. What are we looking at? Summation of dt minus ft. dt minus ft down here is 53.41. Now we have to go through all of these here. Here's your alpha 0.30. The things we went over earlier, we have to go through all these before we take these. We subtract the one from the other. 40 minus 37 is 3. 41 minus 37.9 is 3.10. Now we take the absolute of that. So if this is a negative, this becomes a positive. We add it up. It gives us our 53.41, which is this. Now the time periods are 11. If you notice here, we have n minus 1 in the time periods that we have to use, and that will then come up with, for 12, our mean absolute deviation. And again, the lower that is, the better off, and the more accurate the forecast. And this gives us also a light of magnitude of the data. It sheds a light on it. Now we can also compare the accuracy here, and for these different services. So the exponential smoothing gives us an MAD of 4.04. The adjusted exponential smoothing, if we use an alpha of 0.5, a beta of 0.3, the mean absolute deviation is 3.81. It does a little bit better if we use the linear trend line. The MAD goes down to 2.29. What's the best one? The linear trend line, because it gives us the lowest MAD. We go from exponential smoothing of 4.04 down to linear trend of 2.29. Now, variation on MAD is the mean absolute percentage deviation. This gives us a percentage, and again, we can see below the formula that's necessary. The mean absolute percentage deviation is equal to the same summation here of these different demands and the times. And again, remember we had the 53.41, but we put it over the 520. Again, 53.41, and 520. Here's where these two numbers came from in table 15.8. And what does that give us? It gives us 0.103, or a 10.3%. Again, let's take a look. If we use exponential smoothing, it gives us an MAPD of 8.5. Not bad. But if we use adjusted exponential smoothing, MAPD becomes 8.1. If we use a linear trend model, it is 4.9. Ladies and gentlemen, what's starting to show up here is that the linear trend line seems to do the best. It gives us the lowest MAD and the lowest MAPD. And we also have this cumulative error. Again, this is the summation of all of these errors. It's a relatively large positive value, says the forecast is low. And so if we have a lot of errors and they're positive, the forecast is low. And if it's and vice versa, if the errors are negative, then the forecast is going to be high. It's almost always zero for the cumulative error is going to be zero. It's not a good measure for this method, so again, we take a look here at 15.8, and we can take a look at the cumulative error directly from that is 49.31. 49.31. Here is that error that we had talked about. Okay, so let's continue on. And we also have now some exponential smoothing that we can use. We can adjust this exponential smoothing. We get an error of 21.14. The average error bias is the per period average of the cumulative error. So we can take this, and we had our 49.31. How many of these did we have? We had 11 of them. What does that give us? 4.48. Again, a large positive value of the average error indicates it's biased low. A large negative error tells us that it is biased in a high manner. And so let's take a look here. Exponential smoothing. Let's compare exponential smoothing with an alpha of 0.50, rather the exponential smoothing with a smaller alpha of 0.50 gives us even smaller errors. If we do this adjusted exponential smoothing, then we're going to get even smaller errors, and the trend line, at least for the MAD and MAPD, gives us smaller even yet. So these results are consistent for all of these forecasts. The larger value of alpha is is preferable to the smaller alpha, 0.30, because we're getting a smaller error. Adjusted forecast is more accurate than exponential smoothing, and the linear trend is the most accurate of all these. So let's use the trend. The trend is our friend. Trend is our friend. So, here again, Excel can do all of this for us, and there's a data miner for Excel. We can buy that for a mere $25,000. It will do these also. So we can use Excel. Here again, we can use the exponential smoothing in Excel, and just fill in the spaces, and it will give us, our different seasonality. Here's our seasonality we talked about before. Remember, here was our 148.7. And the linear trend forecast is 58.17, the same number we came up with before. Here again, we can use QM and for Windows, it will give us the same answer. So, time series techniques have one single variable to forecast, and that is time. Regression uses one variable or more than one variable. And the simplest form of regression is a simple linear regression. We can use multiple regression also. So linear regression, we've gone over this before. The dependent variable is y. Independent variable is x. And again, we have an intercept here at A, and we have a slope of the line B. Now, we had shown you how to calculate this B, the slope of the line, the rise over the run before. Here is the intercept. We've shown you how to do that before. This is how we get x bar. We add them all up and divide it by n. Add all the y's up, divide it by n. We get the mean for the x and the mean for the y. Now, let's take a look. We can do this in SPSS. We're going to ask you to do this for the assurance of learning, and we're going to ask you to give us an explanation. So what we're going to say here is that if the number of wins go up, then the amount of attendance should go up. And so here's 4, 6, 6, 8, 6. We add these all up. We get the average of x bar, the average of xy. The average of y bar. You take x times y, we add these up. And so here's where we're going to get our numbers. Take a look here. 2,167.7. X squared is 311. Where are we going to see these before? Add these up and divide it by 7. 346.7 divided by 7. What are we going to get? 49 divided by 1, 2, 3, 4, 5, 6. What are these? 1, 2, 3, 4, 5, 6. 7. By 8. And we should get our x bar from that one. So here again, here's our 8. There are 8 of those periods. 49 divided 8, 6.125. Here's our 346.7. Divide that by, there's 8 of these. And what do we get? 43.34. Here is our, 2167. Where did we get that? Right here. We took x times y and summated them. 2167. This is summation of squares. And if we go through this, we get there that A is equal to y bar minus bx is equal to 43.34 minus 4.6 is equal to 18.46. So this, is going to be where the B subscript 0, where it crosses the line. And so y is equal to some value that we're going to always use, 18.46, plus some value times whatever x is. And so if we have 7 wins, what would we say the attendance is going to be? 46,880. And here's our regression line. Here again is the error where we've missed them. Hopefully there's as much error above as there is error below. And now, here's a correlation, is a measure of the strength of the relationship. It should be somewhere between +1 and a -1. If it's 0, there's little to no relationship. If it's very near to 1, it's a strong relationship in a direct way. And if it's -1, it's a strong relationship in a negative manner, inversely, between x and y, between the dependent and the independent variables. So that's R. So here's how we get R. Again, we've been through this before, and so you can work your way through and find out the answer to this 2,167. You've seen these numbers before in the previous, again, have we not shown these to you before? Here's where we're getting these numbers, right? And n is equal to 8 time periods that we're using. So we've shown you how to get these numbers. And so we get a value here of 0.948. So we have a coefficient of determination. Its percentage of variation of the dependent variable results from the independent variable. How much of the independent variable is telling us what's going on with the dependent variable? And we can square this correlation coefficient, or R. It becomes R squared. So 0.948. Square it becomes 899. So it means that 89.9% of the amount of variation of attendance can be attributed to the number of wins. The more wins we have, the higher the attendance is going to be. And, we still have 10.1% here that might be due to other factors. We might come up with another X, another independent variable that will get us closer to 100%. But at 100%, we could have multicollinearity, which is not a good thing either. So be careful that you are not using two factors to measure the same thing. So here is Excel. We would go through. We can do this analysis. We can also do it in SPSS. It will give us a p-value of 0.000. Again, that small p, less than 0.05, is good. Here's our f-value. The f-value has to be looked up in the back, depending upon the degrees of freedom and the critical value. Bigger f-values are better, but again, it depends upon the degrees of freedom. It depends upon the critical value that you will find. So here again, we can have multiple regression. We can have more than one. And so what else would be involved here with our wins? What else could we have? Well, what happens if we promote it? If we put more money into promotion? We advertise on the radio, in the newspaper, on television. Will that improve our Y? So we have two X's now, wins and promotions, that will lead to what we are proposing, higher attendance. And if we do that, and we take a look at the data, we will see that we will come up with an increase in the attendance if we increase the number of wins and if we increase the amount of advertising that we put into it. So here again is another example of what we had talked about before, another previous example of using the computer software, and we can calculate the MAD and again compute the cumulative error, and it shows us again that smaller errors are better. Smaller MADs, smaller MAPDs, smaller E-bars are all better than larger values. So here again, another example. Here's a quarter, 1 through 10. Building permits, and so as we increase the building permits, will this increase the lumber sales? Go through this whole process again, come up with our formula, of A is equal to Y hat minus BX is 12, right, etc. And this will then, here's our R value. Our R squared is 92.5. Well, our R is 9.925, and we can square that. And what we'll find out is that if we have 10 permits, then this will equal 1,386 board feet of lumber. And so, thank you, ladies and gentlemen. Appreciate your time and effort, and see you again next week at the same bat time and the same bat station. Thank you.